Hello, I'm Catalin Dima from University of Créteil, and I will present our paper on a Hennessy-Milner Theorem for alternating temporal logic with imperfect information, which is joint paper with Francesco Belardinelli from the Imperial College London, Vadim Malvone from Undecidability, and Ferucio Tiplea from the University of Iași, Romania. The outline of this presentation is the following. After briefly recalling the Hennessy-Milner Theorem for the case of classical bisimulation, I will recall several variations of the semantics of the alternating temporal logic with imperfect information and the bisimulations introduced for perfect and imperfect information. Then I will state the Hennessy-Milner Theorem for ATL with imperfect information and concentrate on some elements of the proofs, among which the construction of a four-player bisimulation game with imperfect information and the proof of the determinacy of that game. I will also briefly present the undecidability of bisimulation with imperfect information and then with some concluding remarks and directions for further work. Recall that a bisimulation is a relation on states of one or two transition systems which has the diamond property, stating that whenever state Q can make any transition to state R in the first system, and Q is simulated by state Q prime in the second system, then there exists a state R prime in the second system which simulates state R, and Q prime can make an A transition to R prime. Then Hennessy-Milner theorems for label transition systems has two implications. The first stating that the bisimulation preserves the satisfiability of modal logic. The second, stating that whenever two systems are related by the equisatisfiability relation, then they are bisimilar. So our aim is to adapt this setting to the case of alternating temporal logic and concurrent game structures with imperfect information. ATL is a modal logic for expressing the strategic abilities of coalitions of agents, and its semantics can be given on concurrent game structures, which are label transition systems in which each transition bears a tuple of labels, one action label for each agent. The modal operators utilized by ATL are strategic operators for coalition, and the semantics of strategic operator for coalition A is that A has a strategy for accomplishing some subformula. So for our simple example inspired from matching pennies, two agents having two actions available, each heads and tail, and the winning state being the one in which both agents have played the same action, the formula displayed states the existence of a strategy for Alice to reach the winning state, which is obviously false since neither of the two strategies for Alice may reach only the winning state. This also gives the opportunity to recall the dual operator, which states that in state 0, for any strategy for Alice, there exists an outcome which is not winning. On the other hand, if we look at coalition power, then the two agents, by working together, can reach the win state by agreeing beforehand to play the same action, for example, heads. Suppose now the game proceeds in steps. First, Bob plays and Alice is idle, then Alice plays and Bob is idle. Now Alice has a winning strategy, which is to look at what Bob played and then play the same action. This implies that Alice has perfect information of the system state. ATL with imperfect information introduces agent observability as equivalence relations between states, with two states being equivalent for Alice when Alice doesn't know whether the system is in one state or the other. In our case, it could be because Bob hides his first action from Alice. Then indistinguishability is taken into account at the semantic level of ATL by considering uniform strategies in which agents play the same action at indistinguishable states or histories. So when Alice does not see what Bob played at the first round, she can play only two strategies, heads or tails, after Bob's first move, which means that with imperfect information she is no longer able to win. The same situation occurs when games have multiple initial states with indistinguishabilities. For example, we may abstract from Bob's first action by considering two initial states in the game, each state representing Bob's hidden coin. Then again, Alice doesn't have a winning strategy since none of her uniform strategies is winning in both initial states. The subjective semantics of ATL is a generalization of this situation in that it requires for coalitions to play the same uniform strategy from each state which is indistinguishable for one of the agents. In the displayed example, in state 2, the coalition does not satisfy the formula Alice and Bob can enforce next win, since the unique joint winning strategy is not uniform for Bob between the states 2 and 3, as Bob's winning action in state 2 is different from his winning action in state 3, which can be interpreted as the fact that Bob does not know, when observing state 2, which action he should play. Not, however, that the same formula holds in state 1, since the coalition now does have a uniform strategy applicable in all states indistinguishable from state 1 by one of the agents, which amounts to Bob knowing exactly the initial state. But do really Alice and Bob know that they may win with the subjective semantics? Well, actually no, and we have an example here. With the subjective semantics, Alice and Bob win in state 1 due to the existence of a joint strategy to reach win from the three states 1, 2 and 4. Strategy which is uniform for both Alice and Bob. But Alice is not sure that Bob knows what to play. She knows that the system might be in state 1 or 2, based on her observations, and while in state 1 the existence of a uniform action for Bob is guaranteed, it is tail, which can be consistently applied by Bob in both states 1 and 4, which are the observations that Bob can make of state 1. This is no longer the case in state 2, since based on his observation of this state, which is states 2 or 3, Bob does not know whether to play heads or tails. The common knowledge semantics capture this by requiring that the joint uniform strategy ensures the desired objective in all the states of the common knowledge neighborhood of the state where the formula is tested. So let's see how bisimulations were adapted to the case of perfect information. Assume two concurrent game structures G1 and G2 and suppose we want to simulate strategic abilities of some coalition in state S of G1 with strategic abilities of the same coalition in S prime. In order to guarantee that any objective which is accomplishable in a state S by coalition A is also accomplishable in state S prime by the same coalition, the idea is to have a way to map each joint strategy sigma for A in S to a joint strategy sigma prime for A in S prime, such that when sigma accomplishes some objective phi, sigma prime accomplishes the same objective in S prime. And to do this, we have to ensure that the set of outcomes of strategy sigma prime are included in the set of outcomes of strategy sigma. That is, each run produced by sigma prime in S prime has the same projection on the set of atomic propositions as some run produced by sigma in S. Note the zigzag needed when just proving one-way simulation and the quantifier alternation. For each strategy sigma in the first game structure, there exists a strategy sigma prime in the second game structure, such that for any outcome rho prime of sigma prime, there exists an outcome rho of sigma, such that rho and rho prime have the same projection on the set of atomic propositions. And the way to ensure this in a step-by-step manner is to have a zigzag property on joint actions for a coalition and their outcomes as in the figure. And we arrive at this variant of alternating by simulation proposed by Alur, Henzinger, Kupferman and Vardi for alternating time temporal logic, in which when state S prime simulates state S for some coalition, then for each of the coalition's joint actions in S, there is a joint action for the same coalition in S prime, such that each of S prime's outcomes, T prime, can be mapped back to one of S outcomes, T, in such a way that T prime simulates tail. For the case of imperfect information, we have the following history-based version of a definition from a previous paper, in which when history H prime simulates history H for coalition A, then, first of all, atomic proposition labeling history H prime are the same as the atomic propositions labeling history H, then the simulation is compatible with the epistemic relations like a modern simulation would do, and 3. The simulation is compatible with uniform strategies in a way which generalizes the properties in the case of perfect information and are sketched on the next slide. The place of joint actions in the definition of alternating bisimulation with perfect information is taken by one-step joint uniform strategies for the coalition defined on the whole common knowledge neighborhoods. The idea is that each one-step joint uniform strategy sigma defined on the common knowledge neighborhood of the simulated strategy must be mapped to a one-step joint uniform strategy sigma prime defined on the whole common knowledge neighborhood of the simulating history, such that for any couple of histories which are in the simulation relation and in the respective common knowledge neighborhoods, for example here S2 and S2 prime, we have that each target of a sigma prime transition from S2 prime simulates a target of a sigma transition from S2. For example, T3 prime simulates T3. That is, the simulation of the effect of a joint one-step uniform strategy has to be consistent, has to have a consistent effect on all couples of simulating states in the Cartesian product of common knowledge neighborhoods. Then, a bisimulation relation is just a relation which is both a simulation and a reverse simulation. We may then state the desired form of the Hennessy-Milner Theorem for ATL with imperfect information, which contains two implications. For the first one, if we fix a coalition and we have a bisimulation for that coalition between two concurrent game structures with imperfect information, then any formula which utilizes just the operators for that coalition and is satisfied in a history of G will be also satisfied in a bisimilar history of G prime and vice versa. And the reverse property, if two histories belonging to two concurrent game structures with imperfect information satisfy the same A formulas, then there exists an A bisimulation containing that pair of histories. Note that part 1 holds for all semantics, but part 2 only holds for the common knowledge semantics, and we provide a counterexample for part 2 and the subjective semantics in the paper. The direct property can be proved by easy but tedious induction. So let's go to the proof of the reverse property, for which we introduced a bisimulation game which is played between 4 players organized in 2 coalitions, the spoilers and the duplicators. The spoiler coalition has 2 agents, the perfectly informed P spoiler and I spoiler, which has imperfect information, and we have the same structure for the duplicator coalition, containing P duplicator and I duplicator. The positions of the game are labeled with pairs of histories in the 2 game structures, plus some extra information. The moves of the 4 players simulate the various quantifiers in the definition of the bisimulation, with spoilers simulating the universal quantifier and duplicators simulating the existential quantifier. The compatibility of the bisimulation with the epistemic relations is encoded in the loop between the 2 upper positions as follows. Starting with a pair of histories H prime, which duplicators want to prove bisimilar, P spoiler chooses a history K prime and an agent A in the coalition, such that K prime is indistinguishable for A from H prime. Then P duplicator has to answer by choosing a history K, which is indistinguishable from H by the same agent A. Duplicator must also ensure that the labeling of the history K with atomic propositions is the same as the labeling of the history K prime with atomic propositions. These pair of histories KK prime are gathered together in a set of pairs rho, which can be thought as a partial function from the common knowledge neighborhood of history H prime to the common knowledge neighborhood of history H, not the reverse direction. This stage of the game ends when rho is a total function or p-duplicator fails in her obligation to ensure identical labeling. In the second stage, we include the third property of bisimulations as follows. After the set of pairs rho has been completed, p-spoiler passes the control to I-spoiler, who sees this set of pairs rho and chooses a strategy sigma, which is a uniform one-step joint strategy for coalition A defined on the common knowledge neighborhood of the history H. Then I-duplicator, who sees this sigma and the set of pairs rho, must answer with the strategy sigma prime, which is a uniform one-step joint strategy for coalition A, defined on the common knowledge neighborhood of the history H prime. The control then goes back to the p-spoiler, who replaces this pair of histories H, H prime with another pair of histories K, K prime in the set of pairs rho. And then p-spoiler challenges the p-duplicator by choosing a history L prime, which is in the outcome of the strategy sigma prime for history K prime, sigma prime being the strategy the I-duplicator has chosen previously. Then the p-duplicator must respond with a history L in the outcome of strategy sigma for run K, and the p-duplicator must also ensure that the labeling with atomic propositions of history L is the same as the labeling with atomic propositions of history L prime. Then the play resumes with a new stage encoding compatibility with epistemic relations and with the current pair of histories set to LL prime and the set of pairs rho initialized to a singleton pair composed of LL prime. This bisimulation game has a mirror variation in which spoiler choices are in game structure G, the first concurrent game structure, and p-duplicator spoilers and in game structure G prime, and with a similar dualization of the choices of I-spoiler and I-duplicator. And also p-spoiler chooses before starting the first stage of the game whether to play the displayed variation or the dual variation. Some comments should be made here on the necessity to have the two imperfectly informed players, I-duplicator and I-spoiler. First, game positions must contain an information about the pairs of states which the duplicators want to prove bisimilar. Secondly, the choice of the strategy profile for the A coalition in both game structures must be made independently of the game positions in order to ensure that this is really a uniform strategy for the A coalition. This can only be implemented by utilizing the two imperfectly informed agents, I-spoiler for the choice of the challenging strategy sigma and I-duplicator for the correct answer of the simulating strategy sigma prime. The bisimulation game behaves as expected in that whenever there exists an A bisimulation between two concurrent game structures with imperfect information containing a pair of histories A0, A0 prime, then the duplicators win the appropriate bisimulation game with initial position set to A0, A0 prime. Conversely, if duplicators have a joint strategy to win the bisimulation game starting with this pair of positions A0, A0 prime, then there exists an A bisimulation which contains all the positions compatible with duplicators' strategy. Furthermore, we also define A equivalence as the binary relation on histories of two concurrent game structures with imperfect information, which relates two histories whenever they satisfy the same A formulas. Then A equivalence is an A bisimulation. So in order to settle the reverse part of the Hennessy-Milner Theorem, we have to figure out what happens when there is no A bisimulation, that is, when the duplicators cannot win the bisimulation game. So this is where we have to rely on a determinacy property for bisimulation games. Note that these games are a 4-player version of Yale Stewart games, since spoilers have a reachability objective and there's finitely many choices at each position. So we may follow the proof idea for Yale Stewart games by trying to prove that if spoilers do not have a winning strategy, then duplicators have a defensive strategy, and then observing that a defensive strategy for duplicators is actually winning due to the particular reachability objective for the spoilers. Here, a defensive strategy for a coalition is a strategy that avoids positions where the opponents have a winning strategy. So then the proof works by induction of the depth of the position in the bisimulation game by showing that if position is not winning by the spoilers, then there must exist a move by the duplicators that put the game into a position which is still not winning for the spoilers. The difficulty is that we want this joint strategy for the duplicators to be uniform for I duplicator, but a priori we might have constructed two different strategic choices for I duplicator in two positions, giving him the same information, that is this row set of pairs and this sigma, which is the strategic choice for I spoiler. But let's have a closer look at such a situation. On the left, after I duplicator's choice of sigma 1 prime, P spoiler can change the current history pair to any other pair kk prime in row, with the resulting position still not being winning to the spoiler coalition. Then I duplicator should pick sigma 1 prime 2 at the right position, which has the same information at the left position, and this choice would also be safe there. Hence, I duplicator's defensive strategy can be made uniform. So now that we know that bisimulation games are determined, whenever spoiler coalition wins, we may proceed to identify which formula actually separates the two concurrent game structures with imperfect information. And this can be done in a step-by-step manner by building next time formulas at positions where spoilers are sure to win in one stage, and then nesting these formulas. The I spoiler winning choice of sigma is encoded in the leading coalition next operator. Then all I duplicator answers with one-step strategy sigma prime are encoded in this big conjunction. Then followed by this P spoiler choice of the history K prime, which is encoded in the disjunction of the K prime, followed by the P spoiler's choice of L prime encoded in the last part of the formula. Note that the formulas built here need the yesterday modality, since spoiler's choice of a separating strategy is encoded by the strategic next operator. But then P spoiler's essential move to replace the current history pair by another requires the reference inside this strategic next formula to the previous position just before taking the separating strategy. We also show that the history-based bisimulation with imperfect information is undecidable, and the proof utilizes the technique behind the undecidability of model checking for alternating temporal logic with imperfect information. Namely, we encode each Turing machine which starts with an empty tape as a concurrent game structure. This concurrent game structure is then shown A bisimilar with a simple model in which some coalition has a winning strategy, if and only if the Turing machine holds. In conclusion, we have shown that bisimulations can be adapted to zero-sum games with imperfect information and to alternating time temporal logics with imperfect information, where combinations of alternating bisimulation with perfect information and epistemic bisimulations do not work. We also showed that this history-based bisimulation is undecidable. Two directions for further work are adapting to strategy logics with imperfect information and generalizing to determinacy results to other types of multiplayer games with imperfect information. Thank you.